In this video, which will be quite descriptive and informative, we will talk about black holes, and while explaining black holes, we will also explain some related concepts. A black hole is a region of space-time where gravity is so incredibly strong that light, electromagnetic waves, and nothing else have the energy to escape from it. In 1958, the interpretation that a black hole is a region in space from which nothing can escape was published by David Finkelstein. Since light cannot escape from a black hole and therefore cannot be directly observed with telescopes, astronomers primarily investigate how black holes affect and distort the matter around them. If we explain it in some terminological terms by stating that we will simplify it later, the limit from which there is no escape is called the event horizon. According to quantum field theory, a black body whose temperature and mass are inversely proportional has the same spectrum as its event horizon. If the mass is very high, this temperature is on the order of a billionth of a Kelvin for stellar black holes, and it is impossible to observe directly. Stellar mass black holes occur when massive stars collapse at the end of their life cycles. Black holes have the ability to grow by absorbing mass from their surroundings. Supermassive black holes with millions of solar masses can form either by absorbing other stars or by merging with other black holes. Another formation method is through the direct collapse of gas clouds. Neutron stars were discovered by Jocelyn Bell Burnell in 1967, increasing interest in gravitationally collapsed compact objects. Perhaps due to this increased interest, Einstein put forward his theory of general relativity and predicted that a sufficiently compact mass could form a black hole by deforming space-time. The first known black hole was Cygnus X1, which was identified independently by several researchers in 1971. In order to understand the existence of a black hole, it must either interact with other matter or interact with electromagnetic radiation. Any matter falling into the black hole can form an external accretion disk heated by friction, creating quasars, some of the brightest objects in the universe. Stars that come too close to a supermassive black hole may break into very bright ribbons before being swallowed. Now, after giving some brief definitions, we will tell you about a supermassive black hole in the Milky Way. In astronomy, any of various objects in the universe that emit relatively large amounts of radio waves is called a radio source. The most powerful include pulsars, quasars, and certain nebulas. Rapidly rotating neutron stars are called pulsars. A neutron star forms when the core of a star collapses inwards and squeezes together in a supernova explosion. These stars, composed almost entirely of neutrons, have a diameter of 20 kilometers or less and are extremely dense. It is said that the weight of a tablespoon of neutron stars is more than 900 billion kilograms. Found at the centers of some galaxies, quasars are very high luminosity, gas-powered astronomical objects that rotate at high speed and collapse into a massive black hole. Quasars are among the most distant and brightest objects known. Various tenuous clouds of gas and dust occurring in interstellar space are called nebula. The orbits of stars orbiting a black hole can be used to determine the mass of the black hole and its location. Such observations can be used to rule out possibilities such as neutron stars. With this method, astronomers have identified many stars in binary systems that are likely to be black holes. Going back to the black hole in the Milky Way that we mentioned before, it has been determined that the radio source called Sagittarius A star in the core of the Milky Way contains a supermassive black hole with a mass of approximately 4.3 million times the Sun. So what happens if a person gets a little too close to a black hole? The part of any object falling into a black hole that is closer to the black hole feels a stronger gravitational force than the part farther from the black hole. This difference in gravitational pull increases as the object approaches the event horizon, and the extreme densities of black holes create a spectacular effect. Due to this effect, as the object approaches the black hole, the object becomes increasingly elongated, creating a long, thin shape. This process was first described as spaghettification in theoretical physicist Stephen Hawking's book, A Brief History of Time. Black holes don't just turn things into spaghetti. Just as a black hole can stretch objects, it can also flatten objects like pancakes. This occurs primarily in supermassive black holes and is a phenomenon called the pancake explosion. Eventually, stars that come too close to black holes will be flattened and compressed by tidal forces. and this short-lived pancake distortion will be followed by an explosive release of thermonuclear energy. There is another strange phenomenon that a rover near the black hole will observe. In this phenomenon, called time dilation, time flows slower in places close to the black hole than in distant places. This is because, according to the general theory of relativity, this phenomenon occurs because the black hole's gravity curves space-time in a way that affects all measurements of time and space near the black hole. To simplify this, we can say that if you leave the Earth and go near a black hole, time will flow much slower for you than for those on Earth. This means you will age much slower than those on Earth. A question may be asked, such as, does falling into a black hole mean time travel? The question of whether time travel is possible is always a curious question. It is said that an hour spent near the black hole could be equivalent to years spent on Earth. Thus, it is said that when we return to Earth, we will travel in time and see the future, because according to those who say this, we will only have spent an hour near the black hole. Spending time near the black hole is not possible due to the spaghettification phenomenon we explained before. In addition, in order to cross the event horizon and exit the event horizon again, it is necessary to exceed the speed of light, which scientists say is not possible. Now let's say something interesting. We actually experience a very small amount of time dilation on Earth due to Earth's gravity. So is there any proof of this? Clocks have been observed to be slightly faster on airplanes than on the ground. Astronauts living on the International Space Station also witness this situation at a slightly different pace because they are further away from the Earth's gravitational force. As an object heading towards a black hole approaches the event horizon, it appears to begin moving much more slowly until it appears completely frozen. Some black holes are surrounded by hot rotating material called an accretion disk. Here, gas and dust will collect, form a vortex, and flatten into a disk. The matter in the accretion disk then continues to rotate and fall towards the event horizon of the black hole. As an object gets closer, the gravitational force intensifies and matter continues to separate and spaghettize. And then, as matter in the accretion disk falls into the black hole, it rotates around it, and friction can produce light ranging from radio waves to visible light to X-rays. Sometimes black holes can even direct some of the falling matter into high-speed jets of particles that travel away from the black hole and emit gamma rays, which astronomers can use to find black holes. As a result, matter near a black hole can become spaghettified, superheated, squeezed, pancaked, pulled apart, and spun around while time stretches in unusual ways. However, we do not yet know exactly what will happen when this matter crosses the event horizon and falls into the black hole. If matter falling into a black hole can come out of there, if this matter is a space shuttle, and if a space traveler tells us what happened, only then can we know what happened and what will happen.